Hello, welcome back to my channel. In this video, we'll discuss about distortion of octahedral geometry. This effect is popularly known as Jahn-Taylor effect. The shape of octahedral complex, or you can say the shape of octahedral complexes of transition metal ions are affected when d orbitals are asymmetrically filled. This is the most important word in Jahn-Taylor effect, asymmetrically filled. Repulsion by 6 ligands in an octahedral complex splits the d orbitals of the central metal ion into T2z and Eg levels. In octahedral complex, definitely there are 6 ligands bonded to the central metal ion. When there are 6 ligands, the shape of the complex is octahedral. During formation of 6 bonds with central metal ion, the d orbitals in d subshell splits into T2z and Eg. You know, in d subshell there are 5 orbitals: dxy, dyz, dzx, and ds square minus y square dz square. Out of these 5 d orbitals, first 3 are known as T2z. Last 2 are known as Eg set of orbitals. When 6 ligands approach the central metal ion to form an octahedral complex, T2z set of orbitals go to lower level. You see here these 3 orbitals remain at the bottom and Eg set of orbitals go up, and the splitting between T2z and Eg is known as del O. This is octahedral splitting between T2z and Eg. This is T2z and this one is Eg. Jahn-Taylor effect will not be observed in case of symmetrical electronic arrangement. If d subshell of the central metal ion is symmetrically filled with electrons, then Jahn-Taylor effect will not be observed. This effect is noticed or observed when the d orbitals are asymmetrically filled. If central metal ion has D0 or D10 configuration, then there is no Jahn-Taylor effect with any ligand. If it is D6, then Jahn-Taylor effect will be not observed with strong field ligands. You see, this is T2z, this is Eg, there are 6 electrons, and this is a strong field ligand, or you can say the 6 ligands are strong field ligands. So the difference between Eg and T2z will be more. So these 6 electrons will remain in T2z like this, T2z 6. As it is symmetrically filled, in presence of strong field ligands, there will be no Jahn-Taylor effect. Similarly, in case of D5 and D8 with weak field ligands, Jahn-Taylor effect will be not observed. You see, this is T2z, this is Eg. Suppose there are 5 electrons and the ligand is a weak field ligand, or there are 6 weak field ligands approach the central metal ion to form an octahedral complex. These 5 electrons will remain in T2z and Eg like this. Means this is T2z3 and this is Eg2, and the splitting between T2z and Eg, del O, will be less. So each orbital in T2z and Eg are singly occupied. Each orbital in T2G and EG is singly occupied, or each T2G and EG contains one electron. That is a symmetrical electronic arrangement. So, Jahn-Teller effect will be not observed if the configuration is D5 and the ligands are weak field ligands. In case of D8, and weak field ligands, you see D subcell has 5d orbitals. In presence of 6 ligands, there is splitting of d orbitals. T2G orbitals remain at the bottom, EG orbitals remain at the top. The difference in energy between T2G and EG is del O, O for octahedral splitting. Here the ligand is weak and there are 8 electrons. Let us arrange these electrons in T2G and EG according to Hund's rule. You see, first this T2G will take 1 electron, then this one, 3. As this is weak ligand, the difference in energy between T2G and EG is very less. So 4th electron will be occupied over here, 5th one, then 6th will be here, 7th one will be here, 8th will be here. And this is T2G is 6 symmetrically filled, this is EG2 symmetrically filled. As the electrons are filled in T2G and EG symmetrically, there is no Jahn-Teller effect. No Jahn-Teller effect is observed over here. If the d electrons are asymmetrically arranged, they repel some ligands in the complex more than the other, causing distortion. Distortion means deviation from the normal arrangement. Distortion means the original octahedral complex will be distorted and the shape will be different one than the normal octahedral complex, as some ligands are prevented to approach the metal ions as closely as others. If the d electrons are asymmetrically arranged, they repel some ligands in the complex more than the other, causing distortion, as some ligands are prevented to approach the metal ions as closely as others. Some ligands are prevented to approach the metal ion as closely as others. Some will closely approach, someone will not closely approach the metal ion. Suppose this is the metal ion at the center, some ligands will approach closely and some ligands will not approach closely. EG orbitals point directly to the ligands. Asymmetric filling of T2G orbitals causes a small distortion. So distortion will be more if EG is asymmetrically filled than that of T2G, because in EG the ligands, you see, EG orbitals point directly to the ligands. So asymmetric filling of EG orbitals result in some ligands being repelled more than the others. But in case of T2G, they do not point directly at the ligand. So asymmetric filling of T2G orbitals causes a small distortion in the octahedral geometry. Case 1. If dz square contains 1 electron more than that of ds square minus y square, then the ligands approaching along plus z and minus z will encounter more repulsion than other 4 ligands. You see, in EG, you know, there are 2 orbitals. One is ds square minus y square and the other one is dz square. If dz square means this one contains more electron, contains 1 electron more than that of ds square minus y square, then the ligands approaching along z-axis plus z and minus z This is the central metal ion, and this is plus Z, this is plus Z, and this is minus Z. And if dz square contains one electron more than that of ds square minus y square, then the ligands approaching along plus Z and minus Z will encounter more repulsion than other four ligands. So elongation of bonds on Z axis occurs. So elongation occurs along Z axis. This is called tetragonal distortion. This is called tetragonal distortion if elongation occurs along Z axis. This tetragonal distortion occurs when dz square contains one electron more than ds square minus y square. Case 2, if ds square minus y square contains one extra electron than dz square, then elongation occurs along xy axis. So compression will be observed. If ds square minus y square contains one more extra electron than that of dz square, so compression will be observed along z axis, which is known as tetragonal compression. If dz square contains one electron more than ds square y square, then tetragonal distortion occurs. If ds square minus y square contains one extra electron or more electron than that of dz square, then that is known as tetragonal compression. In D4 with weak field ligands, D7 in strong field ligands, D9 with any ligand, so Zahn-Teller effect. Let us see Zahn-Teller effect in D4. D4 means this is T2G and this is EG. Between T2G and EG, the difference in energy is del O, and this is a weak field ligand, means del O is less, and T2G contains dxy, dyz and dzx. EG contains ds square y square and dz square. For 4 electrons, you can arrange the electrons in this fashion: 1, 2, 3. As it is less, the 4th electron will go up. So this is T2G3, EG1. And here Zahn-Teller effect can be observed because one of the EG orbitals contain one electron more than the other EG orbital. In case of D7, what happens? In case of D7, there is a strong ligand, so the difference del O is more, and the 7 electrons can be arranged in this fashion: 1, 2, 3, then 4, then 5, then 6, 7, 1 will be over here. You see, as it is a strong ligand, the difference will be more. So after completely filling T2Z, EG contains one electron. As one of the EG contains one electron more than the other, so there is Zahn-Teller effect. In case of D9, last one, you see, in case of D9, any ligand is there, no problem. 1, 2, 3, 4, 5, 6, 7, 8, then 9. If del O is less, means weak field ligand is there, or weak field ligands are present over here. And here one of the EG orbital contains one electron more than the other EG orbital. So in case of a strong ligand for D9, you see the difference will be more, del O is more, and you see first 1, 2, 3, 4, 5, 6, then 7, 8, 9. Here also one of the easy orbitals contain one electron more than the other. So Jahn-Teller effect is observed over here. Here it is a weak field ligand, and for this case this is a strong field ligand. Thank you for watching the video till the end.